we are going to study about d block elements. D block elements are those elements in which the last differentiating electron enters into the d orbital of the penultimate shell. What is penultimate shell? If you have total n shells, then n minus d, the previous one, will be called the penultimate shell. Alright, so such elements which have their last electrons entering into n minus 1d shell are called d block elements. Now there is one more term used for these elements, that is transition elements. Now transition elements have slightly different definition. These are defined as elements which have partially filled d orbital in their ground state or in their most stable oxidation state. And I have taken an example here of copper. If you see, copper in the ground state have completely filled 3D shell. So if you have taken the partially filled d orbital in the ground state only in the definition, then this copper could not have been a transition element. But if you take its most stable oxidation state, that is copper 2+, you will find that it has incompletely filled d orbital. That's why it is also a transition element. Now let's see the elements in the d block element. I have written 3 periods here. It is 4th, 5th and 6th period. Alright, and the groups are 3rd, 4th, 5th, 6th, 7th, 8th, 9th, 10th, 11th, 12th. So this is spread from 3rd to 12th group. Alright, the first transition series. It should be actually this is 4th period, this is 5th period, this is 6th period. And if you consider the transition series, this is the first transition series from scandium to your zinc. Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. The very first thing that we will be seeing is electronic configuration. If you see the general electronic configuration of the d blocks elements, it is n-1 d 1 to 10 and s 0 to 2. So if you see the electronic configuration of scandium, it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Now why I have written 4s first and then 3d1? That is because the n-1 d shall have higher energy as compared to ns. So that's why ns is filled first and n-1 d is filled later than that. So the electronic configuration is this. Now if you see for titanium, this much will be the same and it will become 4s2, 3d2. For vanadium it will be 4s2, 3d3, 4s2, 3d4. Now in case of chromium, it should be like this, but if you take the electronic configuration as 4s1, 3d5, it is gaining extra stability here. So in case of chromium, instead of this predictable electronic configuration, it has this electronic configuration. Due to partially filled d orbital, it attains a extra stability. So the electronic configuration of chromium is this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1 and 3d5. So it has s and d orbitals which are half filled, this giving it a higher stability. Hence chromium has our exceptional electronic configuration. Now let's move to manganese. It will have 4s2 3d5. Alright. So moving on to iron, the electronic configuration will become 4s2 3d6, cobalt 4s2 3d7, nickel 4s2 3d8. Now copper should have 4s2 3d9, but similar to that of the chromium, it also gains extra stability if it has one electron in its 4s orbital, and that way it gets the completely filled d orbital. So instead of having this electronic configuration, its electronic configuration is this. So in the first transition series we have two exceptional electronic configuration, that is for chromium and copper. Now for zinc, it will become 4s2 3d10. So these are the electronic configurations for first transition series. Let's move to the second transition series. Moving on to the next transition series, that is 4D transition series, or you can say second transition series. The first element is yttrium. So the electronic configuration is 4d1 5s2. Here it will become 4d2 5s2. Now niobium will have exceptional electronic configuration. So earlier in the first transition series we have chromium and copper which has exceptional electronic configuration. Now in the second series we have much more higher number of exceptions. Niobium will have exceptional configuration, molybdenum will have, ruthenium will have, rhodium will have, platinum, silver. All of these will have exceptional electronic configuration. So let's see what will be the electronic configuration for niobium. It will be 4d4 5s1. For molybdenum it will be 4d5 5s1. For titanium it will be 4d5 5s2. Now for ruthenium it will be 4d6 5s2. No, ruthenium will have exceptional electronic configuration. It is actually 4d7 and 5s1. For rhodium it is 4d8 5s1. For palladium it is 4d10 5s0. For silver it is 4d10 5s1. For cadmium it is 4d10 5s2. So that way we have lot of exception in our second transition elements.